Testing, testing, 1, 2. Yep, that seems to be working. Welcome, everyone, to let me just check the lighting. It still says 50%. I hope that is okay. If you find it too dark, just let me know. Welcome, everyone, to this year's Introduction to Computer Science, Comp 9020, or Foundations of Computer Science, I should say. I will always, every week, have a set of slides that will start with an overview of what we are going to look at. This is going to be the main textbook. R and W stands for the two authors. I will say more about this textbook in just a minute. And I will also point out which chapters and which sections we will be looking at in that week. We will have a weekly problem set or homework for you to do every week, including an assessment of the homework, which is in the form of an online quiz. And these online quizzes, the assessment for the homework, will always be due on the following Thursday, just before the lecture, actually before the help tutorial, which takes place on Thursdays from 11 to 12. Now, the first quiz, as I will also say later, is just practice quiz for everyone to get used to the environment and get used to the type of questions. It won't count for your final assessment, but after that first quiz, all the weekly quizzes, they will contribute, they will have a small contribution to your final mark in this course. I also, because this is a postgraduate course, very much encourage everyone to do self-guided study, especially with the help of the textbook. The main reason for me to choose this textbook is that it contains an abundance of exercises. Many, many pages in every chapter are devoted to exercises. Half the exercises do have a solution in the end, and the other half you're expected to judge your own solution. We will be going through some of the exercises in the lecture, and of course there will be exercises as part of the homework, but I really encourage everyone to make sure that you understand properly what we've been talking about, to look at additional exercises, in particular in this textbook. A few words about me as the course convener and everyone else who is involved in running this course. My name is Michael. If you wondered how to pronounce my surname, the correct pronunciation would be Tilscher, but you can call me Michael. This is my email address. In case, in particular, you have any personal issues to discuss, then you're welcome to send me an email. I also offer 2 consultations every week, and I made sure when I selected these times that none of you, or only very few of you, would be busy during that time according to your own personal schedule. On Monday from 2:30 to 3:30, and on Fridays from 4:15 to 5:15. In particular, I suspect Friday will be good for you because this will be right after the Friday lecture. My office is in the Computer Science Building, K17. Office number is 401J, but this is inside of a secured area. So if you want to see me, you don't have to email me beforehand. You can just come during this time. But you would have to pick up the internal phone and dial this number that is shown here, and then I'll come and let you in. What is my research? I'm a computer scientist. My main research area is in artificial intelligence and robotics, with a particular interest of mine being general problem-solving systems, or artificial general intelligence. And one aspect of this is to try to build general game-playing systems. If you're interested in reading more about this, just Google general game-playing, and then you will find more information. What do I do in my pastime? The 4 Fs. I enjoy to read. I enjoy to watch movies. I do enjoy football, and I, in particular, support my home team, the German national soccer team. But as a good dual citizen, I also support the Socceroos, of course. And I really very much enjoy food. Now, I'm so over German food. If you grew up on German food like I did, then you would understand why. One of the reasons why I really like to live in Sydney is that there's so much variety of different food, in particular, lots of Southeast Asian cuisines that I really enjoy, and in particular when they are spicy. So I am known to go out of my way and to travel to suburbs that are far away. For example, Cabramatta is one of the suburbs that I really like, or Eastwood, just for good food. We do have a tutor, Sahil. He will be running the help tutorial, and he will also help me answer questions on the forum. The help tutorial will always take place every Thursday from 11 to 12. This will be just before this lecture, starting in week 2. This is the location, not too far from here. And I will say more about this help tutorial in just a minute. His email address is shown here, and then we've also got a course administrator, and occasionally you might receive an email on organizational issues by Michael. A few words about the course aim. The course aims to increase your level of mathematical maturity to assist with fundamental problems that we deal with in computer science, namely finding, formulating, and proving properties of specifications of problems and programs that we write in order to solve these problems. What's going to be the actual content? It is taken from a list of subjects that constitute, as you can say, the basis of a toolbox that every serious computer scientist needs to know. And I'm listing the different topics that we will go through here on this slide. Now, you will see that this is a course that focuses on mathematics. It's not a programming course. There is 9021, the Introduction to Programming, which is meant to introduce you to actual programming. This is a course that focuses on the mathematical foundations for computer science. You might recognize some of these areas, and one of the difficulties of this course is that for some of you, some of these topics might be very familiar, and you might find that there isn't too much new in these topics. They had to be chosen, however, in order to make sure that after this course, everyone has reached the level of mathematical maturity to apply everything that we're talking about in other more advanced courses. I should also mention that you may not always immediately see where some of the things that we're talking about will be applicable, and this is why I've also copied this additional remark. We are at a university. University, the word derives from a Latin word which stands for the sum of all things, or a whole. And I'm saying this because by acquiring knowledge about these mathematical foundations and enhancing your problem-solving skills, which is really what we're going to do as we go through this course, then you will prepare yourself for the future. I can see that this is not really properly displayed here. I want to make sure with the next couple of slides that I'm not using the very bottom of the slide. Here on the screen, I can actually see everything, including the last line, and I suspect that the lecture recording will record what is seen on the screen here and not what you in the audience can see here. Anyway, I'm saying this because we will be looking at lots of problems to solve with the help of these mathematical tools, and just by training yourself to solve these mathematical problems, you are preparing yourself for the future as a computer scientist, even though some of these topics we will be talking about for you personally might not be immediately applicable to problems that you're dealing with in other courses. The course material is placed on this main course webpage. You need to log in with your ZID and ZPassword in order to access this course page. The textbook that we will be mainly using is called Discrete Mathematics by Ross and Wright, and it is this book here. Let me see if that works. Discrete Mathematics. Not sure if you can see the authors. They are down here. If you look at this book, it's got, let me see how much, around 600 pages. We will not be going through all these chapters. If you look at what I had on the previous slide, the contents, you will see which chapters we will actually be covering. But of these 600 pages, a lot, maybe 20%, even more, is devoted to exercises. This goes back to what I said earlier, that this book has been chosen in particular because it provides a lot of exercises. There will be one or two minor topics that are not covered in this book, for which I have a supplementary textbook, and in any case it might be of interest to look at this supplementary textbook because it deals with a lot of topics that are also dealt with in the main textbook. And it might just be interesting to read an alternative view on the same topic. This book has the advantage that you can download it for free. If you click on the link here, then it will take you to a PDF that you can download. We will be having lectures as well as problem sets and assessments for problem sets, namely quizzes. The lectures will present the theory and demonstrate problem-solving methods with a good number of examples in every lecture. I will always make sure that the lecture slides are available before the lecture. Typically, I will try to have them ready Tuesdays. And then you're most welcome to look at the slides before you even come here to get an idea of what we will be talking about. You're most welcome to interrupt me at any time if anything is unclear and you want to clear any of the doubts that you have. Raise your arm and ask a question, and then I will try to answer it. But we need to make sure that we get through the contents of this course, so this should never lead to idle chatting. This is the one major component, the lectures. The other major component is the weekly homework and the assessment of the homework, the quizzes, which aims to clarify any problems that you might have with the lecture material and for you to work through exercises that are related to lecture topics. Also, the homework, called problem sets on the webpage, are made available before the lecture. Sample solutions will always be posted in the following week, but of course it's very important for you to do the homework yourself and not just wait for the sample solutions. First of all, because of the weekly assessment, obviously the sample solutions will only be published after the deadline of the weekly quiz. And also by looking at solutions, you might easily say, oh, I could have done that myself. But understanding a solution is very different from trying to come up with the solution in the first place. So it's really important for you to not only look at the sample solutions, but always attempt to do all the exercises yourself. Do them yourself and also make sure that you don't fall behind. Make sure that every week you do these exercises and make sure that you understand everything that we've been talking about. Speaking of the problem sets, you find them on the course webpage. I'm sure everyone will have looked at the course webpage already. There is a link to the lectures and a link to the problem sets. And here you will find the weekly problem set, which will typically consist of 5 questions or 5 exercises to work through. Plus, and I should point this out, there will also every week be a so-called challenge exercise. Now, the challenge exercise is for everyone who finds the first few or the first 5 regular exercises a bit too simple, partly maybe because you're already familiar from your previous studies or even from high school with some of these topics. Then I will always challenge you with this challenge exercise, which is always related to the topic of that week and which, at least I hope, is much more difficult than the regular exercises. You don't have to solve these challenge exercises at all. They will never be examinable, and they really go beyond what you're required to understand and know for this course. But for everyone, as I said, who finds it easy enough to solve the regular exercises, you might find that interesting to solve as a challenge. At the end of the problem set, you will find a link to the assessment of the homework. Here I have made that important comment that for the first week, the assessment does not count for your final exam, for your final mark, just in order to make sure that you familiarize yourself with the environment and the type of quiz questions and the type of how they are being evaluated. I suggest that you do click on this evaluation that will take you to the Moodle webpage for this course. The Moodle webpage is different from the main course webpage. It provides a link to the lecture recording. As you can see here, you can access the lecture recordings, which should typically be published right after every lecture. It takes them typically only a few minutes before they are made available. And you will be able to access the weekly quizzes. Now, the weekly quizzes, as you can see here, are always due on Thursday, as I said before, at 10 a.m. Again, I'm repeating here that the first quiz does not count and is meant as practice. When you click on it now, you will see that the quiz is not yet available. The quiz will automatically open right after the Friday lecture. But of course, you need to do the homework first before you can do the quizzes. Right, back to the slides. Oh, I should say the Moodle webpage, when I clicked on the link for the assessment, I was automatically taken to the quiz. What would typically happen is that you have to log into Moodle first with your ZID and Z password. I've done that before the lecture, and this is why it took me directly to the quiz. But don't be surprised if it says that the course is not available unless you log in, and you have to log in separately from the main course webpage. Now, I've already said that the weekly assessment will count towards your final mark for this course. In total, we will have 8 weekly assessments. The first week doesn't count, and we won't have a quiz or homework in week 6 because of the midterm exam, about which I will say more in just a few seconds. So we have got 8 quizzes. Every quiz will be worth 2.5 marks, so the maximum mark that you can get will be 20. We will have an online midterm test for 1 hour during the lecture time in week 6, and the maximum mark there will also be 20. And we will have a written exam, 2 hours in the exam period with a maximum mark of 60. Now, what's important is that the overall score and mark and grade for this course will be determined as the maximum of these 4 possibilities. Either I'm going to add up your results for the weekly quizzes for the midterm and the exam, or I will take any of the other expressions, including I might also take the 100 times exams divided by 60, which means that I will scale up the exam mark in case your exam is better than the weekly and or the midterm result. So what all that actually means, if you don't understand the mathematics behind it, it actually means that if you do better in the final exam, then your weekly quizzes and or the midterm test result will be ignored. I'm doing that only once for the very first course for everyone who is new here. But still, I strongly suggest that you do try your best with the weekly homework as well as the midterm, because many of you will find it easier to do it at your own time, the homework, and score well in the midterm than in the final written exam. So the quizzes and the midterm tests, they can only improve your result, which is why it's still a good idea to try and attempt them. And for everyone who can't be here, and as a matter of fact, we are a much larger class than it seems to be when I'm looking around here. A lot of students, unfortunately, because of travel restrictions, can't be here. If you can't be here and you're listening to this, to the lecture recording, This course has been designed so that you can study it remotely as long as you can't come to UNSW in person. You will have the lecture recordings that you should listen to every week right after the lecture. You have the weekly quiz that can be done online from wherever you are. And you've got the online midterm assessment, which can also be taken from wherever you are with a good, stable internet connection. However, you need to be here for the written final exam, which will take place during the examination period in mid-May, or the latest, if you still can't be here in mid-May, you have to be here for the supplementary exam, which will be sometime in the last week of May. So the good news was that I'm taking the maximum of these 4 possibilities. The other restriction, however, will be that in order to pass the course, your overall score must be higher than 50. That is half the marks that you can get with any of the 4 possibilities. But also your mark for the final exam must be 25 or higher. This is an additional hurdle, an additional condition that you need to satisfy. 25 is around a little more than 40% of the 60 that you can acquire, that you can get in the final exam. The online assessment, I think I've said that twice already, opens every week after the Friday lecture and is always due on Thursday, 10 a.m. in the following week. You will see that you will get your own individual questions for the quiz. Each quiz is worth 2.5 marks, so that the maximum quiz mark is 20 with 8 quizzes that count, given that the first week quiz does not count and should just give you practice. The midterm online test will happen in week 6 on Friday for 1 hour during the lecture time, or more specifically between 2:30 and 3:30 p.m. Again, you will get your own individual questions. Some of these questions will be multiple choice questions. Some will be descriptive and analytical with open answers, and then you're supposed to type in your answer. The maximum midterm test mark will also be 20, and it will also contribute to your final mark, unless, again, your result in the final exam is better than your midterm exam. Nonetheless, the midterm exam will be an ideal opportunity for you to see whether under examination conditions, that is under a certain time pressure, which you will also have for the final exam, you are able to answer exam-style questions on any topic that we have looked at until week 6. Then there will also be a tutorial-style help session, which aims to help you if you have difficulties with the weekly homework, or if you have any other questions related to the course contents that you would like to ask our tutor. These will be on Thursdays, as I said before, from 11 to 12 in the electrical engineering building, room G23, starting from next week, obviously, in case you have any questions about this week's homework and its solution. The attendance of this help tutorial is entirely voluntary. You certainly don't have to go there, in particular if you understand everything perfectly and you found it easy enough to do all the weekly exercises, then there's no need for you to go to this help tutorial. But if you do want to get an explanation, discuss topics, then you're most welcome to come to this help tutorial. Yeah, that was actually the last slide that I had before we can actually start with the mathematics in the first part of this course. But before that, any questions?
Do quizzes have time restrictions?
Sorry, say? Oh, quizzes.
Yeah.
So quizzes don't have a time restriction. You can, once you have done the homework, you can click on the quiz. You look at the quiz questions, and you can look at all these questions, and then you still have until Thursday, 10 a.m. to answer these questions. Everything that you type in will be saved when you exit, and only when you submit your final solutions, then you will have finally submitted. your quiz. And it will ask you 2 or 3 times whether you are certain that you want to submit your questions before you then finally submit.
Yeah, like for the midterm exam, the descriptive analytic questions will be like handwritten or like will type?
No, this will all be online and will all be typed in. I will prepare 2 or 3 practice questions that will show you how it will actually look like. So there will be a mock midterm the week before, which you can then do, and it will all be marked, but not assessed, of course, and that gives you a very good idea of what we expect you to type in. Any other questions about the assessment? Yep.
How's the difficulty of the quizzes versus the midterm versus the final?
That is a very good question. I would say that they tend to be more difficult than the midterm and then the final, simply because you've got much more time.
Yeah.
The homework questions, I'm expecting, I should say that the expectation generally for courses like this with 4 hours of lecture are that you spend around 12 hours per week on this course. This includes 4 hours lecture, then another 4 hours to possibly watch the lecture recording, to go through the slides again, to make sure that you understand everything in detail, and then another 4 hours to do the homework and the assessment, the quizzes. Of course, you've got the whole week to do the quizzes, so the homework questions tend to be a bit more difficult and require a bit more work, sometimes than the midterm and the final. Generally speaking, if you feel very comfortable with all the homework questions and with the quiz questions, then I can assure you, you will find it easy to do the midterm and the final exam. Mm-hmm.
Should I hand in the homework or just the quiz?
No, the homework will not be handed in. This is a feature that all our postgraduate courses have. We don't have individual tutorials or computer labs, certainly not computer labs for this course, but also not individual tutorials. We rely on your self-guided studies. So you do the homework yourself, and the only thing that you hand in is your assessment in the form of quizzes. Now these quizzes, as you will see when you open the first quiz, they will have lots of multiple choice questions related to questions in the homework, or sometimes it will be variations of questions in the homework, and sometimes there will be an open answer, but an open answer will just be a short string or a number. Whereas some of the homework, you will see later, will require you to write short proofs. And this is not something that we can assess with these automatic online quizzes. Then in this case, you're assumed to be able to judge your own solution and possibly compare it with the sample solution that will be published online later. Any further questions? All right, very good. Then let's start with what we want to look at in this first week. We will be looking at an introduction to very basic mathematics. Much of this I'm sure most of you would know already. The purpose of this is going to just make sure that we are all using the same notation, mathematical notation, which other courses at this university in computer science will also be using, to clarify some of the concepts that you may not have seen in your previous studies before. First thing we will be looking at is numbers. We, in computer science and mathematics, we typically distinguish, in particular, integers, for which the standard notation is this slightly weird way of writing z for the integers, which are both positive as well as negative numbers. -2, -1, 0, of course, is also an integer, 1 and 2. We distinguish this from real numbers, which can contain fractions and irrational numbers. The standard notation for the set of real numbers is this slightly funny way of writing capital R. Then one of the uses of these sets is to define functions that map elements from one set to another set. And these are two functions that are very important for computer science in particular, because we often deal with integers, simply because integers can be encoded, unlike real numbers, without having to approximate them on a computer. For turning a real number into an integer, there are two functions that we computer scientists use a lot. One is called the floor, and the other is called the ceiling of a number. Now, the floor is denoted by this is a standard syntax. The floor of a number maps a real number into an integer and is defined as the greatest integer that is not larger than the number itself. And the ceiling of a number, denoted with this symbol, these two symbols, is the least integer that is greater or equal to x. Now here's two very simple examples that should make it very clear. The floor of the most famous mathematical constant, pi, is 3. If you know what pi is, it's 3.14, and so on and so forth. So it's a real number, and what's the nearest integer that is smaller or equal to x? It is obviously 3. So the floor of 3.14 is 3, and that happens to be the same as the ceiling of what you can call the second most famous mathematical constant, namely the basis of the natural logarithm, or e, the value of which is 2.71, and so on and so forth. And clearly, the next higher integer of 2.71, etc., would also be 3. So you can see that pi and e are real numbers. They are not integers. The floor and the ceiling, however, of every real number would be an integer. Now, what can we do with floors and ceiling? First of all, one important property with negative numbers, one has to be a little careful, because the floor and ceiling sort of turns around when you look at negative numbers. Why is that so? If you take the floor of minus 1.5, say, then this would be minus 2, because it's the integer below minus 1.5. And it wouldn't be minus 1, because that would be above minus 1.5. It has to be smaller than minus 1.5, and therefore it's minus 2. Now that would be the same as taking the ceiling of plus 1.5. Ceiling of what? Plus 1.5, the next largest integer would be 2. And therefore we see the floor of a negative number is always minus the floor of a positive number. And vice versa, if you take the ceiling of x, then that would be minus the floor of minus x. Also, we have a simple property. If you take a real number x and you add to it an integer, then the floor or the ceiling of the result can be obtained by, first of all, computing the floor or the ceiling of the real number and then adding the integer to it. This is not true if t is an arbitrary number, but it is always true of an integer. So if we take the floor, for example, of 1.5 plus 2, then this is the floor of 3.5, which is 3, and that would be the same as taking the floor of 1.5, which is 1, plus 2, and that's also 3. What are useful things we can do with the floor or ceiling function? Here's an interesting fact, a mathematical theorem. If you ever wonder how many numbers between two given numbers are divisible by a third number, for example, you want to know how many numbers between, let's say, 5 and 15 are divisible by 3, then you can certainly count. You can say between 5 and 15, we've got 6, we've got 9, we've got 12 and 15. So it's 4 numbers that are divisible by 3. But if you have a very large interval, then counting these numbers might be more difficult than applying this nice formula here, which tells you exactly how many numbers between n and m in this interval are divisible by k. And you can see it does use the floor and ceiling function. Let's try this with an example. Suppose we want to know how many numbers in the interval, what did I say, 5 and 15, are divisible by 3. So our k in the formula is 3, our n is 5, and m is 15. Does it work? It does too. Now, what does the formula say? It says we have to, if we want to know how many numbers in this interval are divisible by 3, we have to calculate the floor of m, which is 15, divided by 3, and subtract from it the floor of n minus 1, which would be 4, also divided by 3. Now, what's the floor of 15 divided by 3? That's 5. And the floor of 4 divided by 3? 1. So we've got 4 divided by 3, 4/3. It's 1.333. And the floor of it would be 1. So indeed, we get 4. And this is exactly what, when we count the numbers ourselves, we would get as a result. It's a nice formula. And it might be a good idea for you to try it out with larger intervals and see if you can then use this formula to count. If you want, you can even write a computer program that then tests your result by actually counting it so that you don't have to do it manually. But you don't have to use a computer program. You can apply this nice and simple formula to obtain the result. Let's have another look at simple exercises just to make sure that you paid attention and understand. These exercises, by the way, they are taken from this textbook. And you will always recognize this when you see an exercise number like this. It means exercise number 4 in chapter 1, section 1. The reason I'm saying this is not only that you can find this exercise in the book, but in particular that you know where to find this type of exercises. And seeing that this is exercise number 4, of course, suggests that there are other exercises similar to these ones. And if you would find it interesting to solve similar exercises, then this is exactly where you would be looking for. Can anyone provide the answer to the first question? What is 2 times the floor of 0.6 minus the floor of 1.2? Minus 1. Everyone says minus 1. Yep, this is exactly right, because the floor of 0.6 is 0. 2 times 0, of course, is 0. And minus 1.2, the floor is minus 1. So 0 minus 1 is minus 1. And if we take the ceiling instead, what is the result? 0. Does everyone agree? Yes, it is 0 because it's 2 times 1 minus 2. 2 minus 2 equals 0. What about this? Square root of 3, the floor, minus the ceiling of square root of 3 minus the floor of square root of 3. What is the square root of 3? We don't even need to know this. All you need to know is that this is a real number that is not an integer, and therefore the answer is indeed 1, as you said. For every number such as pi, 3.1, the floor would be just 1 higher than the ceiling would be 1 higher than the floor, and therefore the result is always 1. All right, that was probably a bit too trivial. Can anyone provide an example for numbers x and y so that the floor of x, or yes, the floor of x plus the floor of y is smaller than the floor of x plus y? 1.5 and 1.5 and 1.8. Yes, very good example. 1.5, the floor would be 1. 1.8, the floor would also be 1. So when you add that up, it gives you only 2. But if you add up 1.5 and 1.8, then this is 3.3, and the floor would be 3. So any two numbers that are greater or equal to 0.5, they will have this property. It sounds a bit strange given what we had here, where we said that we can calculate the floor in this way. But remember that this applies only to integers and not to real numbers. And when you have real numbers, this is no longer true. And what you actually have is this property here. And here's another example that has the exact same property. As a matter of fact, this is slightly smaller than 0.5, but this is large enough so that the sum of the two is actually larger, namely 12 when you build the floor, than building the floor of these two numbers to start with. Another important concept that we need for integers is divisibility. Divisibility, I'm sure most of you would also know what this is, means that you can divide one number by the other number without any remainder. The standard notation for saying that m is a divisor of n is to use this bar, this vertical bar, between m and n to say that m is a divisor of n. And the definition of being a divisor means that you can obtain the number n by finding a third integer k, so that k times m equals n. A simple example, the number 15 is divisible by 5, or 5 is a divisor of 15. What would be the k that you need in order to make sure that this is the case? It would be 3, because 3 times 5 really shows, because it equals 15, that 5 is a divisor of 15. And of course, it also means that 3 is a divisor of 15, because you can find k equals 5, so that 15 equals 5 times 3. Other ways of saying the exact same thing is that 15 is divisible by 5, 5 divides 15, or 15 is a multiple of m. And if you want to say that m is not a divisor of n, then you can use this notation here. Now, this is all very standard. What might not be familiar to everyone is that the notion of divisibility applies to all integers, not only positive, but also negative integers. We also have that minus 5 is a divisor of 15, because you can find another integer, minus 3, so that minus 5 times minus 3 equals 15. It also applies to special cases like 1. 1 is a divisor of every number. Minus 1 is also a divisor of every number. Why is that? Because you can always multiply 1 with the number itself and obtain the number. Every number is a divisor of itself, and every number is a divisor of minus m. So 5 would also be a divisor of minus 15. For 0, and now this might really be a bit tricky. For 0, you have to formally apply the definition in order to see that every number is officially a divisor of 0. So 15 is a divisor of 0. Why does it have to be a divisor? Because you can find a k so that 0 times k, that n times k, 0 times m, 15, is 0. The other way around is we never have that 0 is a divisor of n, because you cannot multiply 0 with a number to obtain a number n. 0 can't be a divisor of 15 because you can't multiply 0 with anything to obtain 15. Unlike the other way around, you can always multiply a number to obtain 0. Except n equals 0. And this might be the most unusual case. 0, by definition, is a divisor of 0, simply because it satisfies the definition. Yes?
Can we divide 0 by 0?
You can divide 0, you cannot divide 0 by 0. This is not what I'm saying here, because when you say, can you divide x by y, you're asking the question, is there a unique result? And typically, the unique result that you would obtain when you ask the question, for example, is 5 a divisor of 15, then there's only one k that makes sure this is the case, namely 3. So you would naturally say when you divide 15 by 5, the result would be 3. However, all this says is that it satisfies this definition, and 0 is a divisor of 0, without us saying that there is a unique k that you could obtain as a result. Because 0 divided by 0 would be satisfied for all k. 0 equals 15 times 0. And this is why we are not allowed to divide 0 by 0, but by definition 0 is a divisor of 0, even though we don't know what the result would be if you do the division. That does apply logic, and it actually is an important question because it goes to show how, in particular for boundary cases, we have to be very clear about how to read these definitions. Now, you would also, I'm assuming, know that numbers greater than 1 that are divisible only by 1 and by itself, they are called prime numbers. Prime numbers are 2, 3, 5, 7. 9 is not a prime number because 9 is divisible by 3, and so on and so forth. Are there any questions? Otherwise, I would like to ask you not to be talking while I'm talking. Thank you. Now, this is what I said, prime numbers. Then we also have the concept of the greatest common divisor, which would be a divisor that both m and n have in common. For example, 15 and 10, the greatest common divisor would be 5, because 15 is divisible by 5, 10 is divisible by 5, and it's the largest number that is a divisor of both. Sometimes, of course, you can have numbers m and n so that the greatest common divisor of m and n is 1. This is certainly the case if m and n are prime numbers, but it might also be the case when m and n are not prime numbers, in which case these numbers m and n are called relatively prime. Does anyone have an example of non-prime numbers that are relatively prime? 6 and 7. Now 7 is a prime number. 6 indeed is not a prime number, but do you have two non-prime numbers that... No, 13 doesn't count and 5 also. I'm looking for non-prime numbers. 8 and 9. Yes, 8 and 9 are good examples. 8 is not a prime number. 9 is not a prime number. But they don't share any divisors except for 1, and this is why 8 and 9 are relatively prime. We also have the concept of a least common multiplier, which is kind of the opposite of the greatest common divisor. The least common multiple is of m and n, a number, so that m is a divisor of that number and n is a divisor of that number, and it is the smallest number that satisfies this property. Simple examples would be, let's say, 5 and 3. The least common multiple of 5 and 3 would be 15. In this case, it is 5 times 3, but there are also numbers where the least common multiple is a divisor of the product of these two numbers. The greatest common divisor and the least common multiple, by definition, are always taken as positive, and this is just by definition, even if m or n is negative, just so that we can be sure that the question, what is the greatest common divisor or what is the least common multiple, has a unique answer. So the greatest common divisor, please, if there is a question, just ask. So the greatest common divisor of minus 4 and 6 is just the same as the greatest common divisor of 4 and minus 6, of minus 4 and minus 6, and 4 and 6. It will always be the positive number 2. Same with the least common multiple. The least common multiple of minus 5 and minus 5 is not minus 5, although this is smaller than 5 and is a common multiple, but by definition it always should be 5. Now coming back to your question with can we divide 0 by 0, the answer is greatest common divisor of 0 and 0 is undefined. And this is important to note as a special case. Why does it have to be undefined? Because we can define or find arbitrarily large k's that we have that 0 times k is always 0. And therefore, there is no greatest common divisor. It can be an arbitrarily large number. We have to make sure that we treat this as a special case, and by definition, we say greatest common divisor of 0 and 0 doesn't exist. And that tells us that you can't divide 0 by 0. Why is that important? If you will be studying, for example, cryptography later, then you will see that number theory, the study of prime numbers, the study of relative prime numbers, and divisibility is becoming very, very important. Cryptography is all about finding very large numbers and trying to calculate or making sure that you can't, in finite time, in practice, find divisors of these numbers. There's one more function that I want to introduce at this point. The absolute value of a number is denoted by these two vertical bars. The absolute value of x is simply x if the number is greater or equal to 0, and minus x if x is smaller than 0. So the absolute value of 3.5 would be 3.5, and the absolute value of minus 3.5 would also be 3.5. So it just gives you the positive part, so to speak, of a number, which can be both an integer as well as a real number. Another interesting mathematical fact is that when you multiply the greatest common divisor of two numbers with the least common multiple of these two numbers, then this will always give you m times n, or since we want to extend this to cover integers, which can be negative, it will actually have to be the absolute value of m and n that you multiply. So if you take the greatest common divisor of, let's say, what did we have, 10 and 5, 10 and 15, or minus 10 and minus 15, and the least common multiple of 10 and 15, or minus 10 and minus 15, then this would be what? The greatest common divisor of 10 and 15 is 5. And the least common multiple is 30. So if you multiply 5 by 30, the result is 150. And if you multiply the absolute values of 5 and 10 and 15, or minus 10 and minus 15, you will also obtain 150. So another nice mathematical fact, and at this point I've been talking for exactly 55 minutes. I always like to have a short break of about 5 minutes between the two parts of a 2-hour lecture. So we will have a break of about 5 minutes, and then I will start at 1:05. Just 1 second. Okay. Let's continue. Everyone. Thank you. Now, one question. Can I get everyone's attention, please? Everyone. Can you please do me a favor and stop talking? Right, so one question that I got during the break was where to find these slides that I'm going through here. You can find them on the main course web page. If you go to lectures instead of problem sets, then there's actually two versions that you can look at. The first version is the slides as I'm presenting them here, and it might be a good idea if you want to page through these slides yourself to use these. If you want to print the slides and you prefer to have them printed to go through them, then I've also put them in this format, 4 slides on 1 page, and this is for actual reading on paper and for writing on them much more convenient, I would say. The other question that I was asked is, if there's a proof for this result. Surely there is a proof. I'm not going to prove this theorem here in this course. We will be proving some properties, and in fact there will be one coming up very shortly, but not everything will be proved. If you're interested in proofs for some of the results that I'm putting up during this course, then most of these proofs you will find in the textbook in the corresponding chapter. Let's have a look if we all are on the same page with regard to these concepts of devices. True or false, and again these exercises are taken from the book. True or false, is n a divisor of 1 for an arbitrary number n? Is that true or false? False, yes. N is not a divisor of n, with only one exception. 1 would be a divisor of 1, but you don't have that 5 is a divisor of 1. Is n a divisor of n? Always the case, yes. And would n be a divisor of n squared? Yeah, that is also true. You can obviously multiply n by itself to obtain n squared. What is the greatest common divisor of 0 and n? I hear 0, I hear n, I hear 1. I hear it's not defined, so we have 4 possibilities now. Think about it. Greatest common divisor of 0 and n. What did we say about divisors of 0? Do they exist? Everything, yes, everything is a divisor of 0. Remember that we have defined everything as a divisor of 0. Because you can always multiply any number n with another number, namely 0, to obtain 0. So this is a tricky question. We do know that every n is a divisor of 0. Now, knowing this, again the question, what is the greatest common divisor of 0 and n? It is n, yes. It's not undefined, it is n, because every number is a divisor of 0, and not every number is a divisor of n, but the largest divisor of n would be n.
So
what if n equals 0? That is correct, it would not be defined. Greatest common divisor of 0 and 0, we have said, is not defined, so the greatest common divisor of 0 and n would be n in all cases where n is not 0. What about negative numbers? So we have to be even more precise. The greatest common divisor of 0 and -2 would be? It would be 2, yes, because we've said we always define this as positive, and therefore the greatest common divisor of 0 and any number n, which is not 0, would be the absolute value of n. Okay, now that was really tricky, but the correct answer is absolute value of n unless n is 0. Let's have a look at a slightly simpler question. Can two even integers be relatively prime? No, they can't be relatively prime. If you have two even integers, like 6 and 8, then 2 is a divisor. And then they can't be relatively prime, because relatively prime means the largest divisor that they have in common would be 1. Now, suppose that m and n are positive integers, and we are given that the least common multiple of m and n happens to be m times n. Is there anything that we can say about m and n if that is the case? They are relatively prime. Yes, they are relatively prime. Very good. That is because we have said that the least common multiple of m and n times the greatest common divisor of m and n equals m times n. So if the least common multiple itself happens to be m times n, then the greatest common divisor has to be 1, because then we have 1 times least common multiple is m times n. That follows from this fact here. If we know that LCM mn is m times n, then the greatest common divisor has to be 1. In other words, they have to be relatively prime. So you would know that for 6 and 8, for example, the least common multiple has to be smaller than 48, 6 times 8. There has to be a common multiple that comes before 48, because the greatest common divisor of 6 and 8 is 2 and not 1. What can we say if someone tells us the least common multiple of two numbers m and n happens to be n? M is a divisor of n. Yes, this is exactly right. M divides n. And the answers are given here. We, in particular, have this result, the absolute value of n, provided that n is not 0. And one thing that I don't think I mentioned here with negative numbers, we also have that -1 is a divisor of 1. Other than that, it's exactly the answers that you gave. Very good. Now, let's have a look at one algorithm that is actually very old. It's named after its inventor, the Greek philosopher Euclid. It's a nice and simple algorithm to compute for any two given numbers, m and n, the greatest common divisor. And it uses a recursive way of computing the greatest common divisor, which is defined as follows. We have a function called f, and f does compute for us the greatest common divisor of m and n, defined as it returns m if m and n are the same. Otherwise, it calculates recursively the common divisor of m and n by saying that if m happens to be greater than n, then subtract n from m and compute the greatest common divisor of the result with n. Or if n happens to be greater than m, then you subtract the smaller number m from n and take these two numbers. Now, let's first of all have a look at how this algorithm works, with only one example, just to get an idea of how and why this algorithm does compute the greatest common divisor of two numbers. Let's say we take the greatest common divisor of, say, 70 and 42. Might actually be good numbers. What should be the result? What's the greatest common divisor of 70 and 42? 7, haha, no. 14, yes. So 14 is the greatest common divisor. and not 7. 7 obviously offers itself when you look at these two numbers, but you can also see they are both even, so they are also divisible by 2, so the expected result is 14. Now let's apply this algorithm to this particular pair of numbers. Now the first case doesn't apply, which says that the result is just m if the two numbers are equal. They are not equal. What we have to do is we have to see which other case applies. We see that the first number is actually greater than the second number. M is greater than n. So we have to replace this by, I'm not using f here, I just use GCD because this is what we're actually computing, is the same as the greatest common divisor of, what is the first argument? So 70 minus 42 is 28, that's correct. And the second argument is still 42. Now, according to the definition, how would the algorithm proceed? Now we see that the numbers are still not equal, but now the first number is actually smaller than the second number. So we keep the first number and subtract the first from the second, which results in 14. And then we clearly see that we are back to the case, not number 1, but case number 2. The first number is greater than the second, so we subtract 14 from 28. 14 and 14. And now we have reached the, as we call it, terminating condition of this algorithm, because now the two numbers are equal, and the result, therefore, by this first case, when the two numbers are equal, should be 14. So as we expected, after some thinking, where we thought 14 should be the result, it really is the result of this algorithm. What can we say about this algorithm? Well, we can say it does work with these two numbers, 70 and 42, but that, of course, doesn't tell us anything about the actual correctness of this algorithm. Does that work for any possible pair of numbers? We can try other pairs, and of course you will see that it does work for other pairs of numbers also, but just looking at a few examples, even if you look at a lot of examples, may not satisfy us as computer scientists when we look at an algorithm. What we really would like to see is whether we can prove that the algorithm is correct for any two numbers, no matter what we input. So instead of running lots of experiments, we want to have a mathematical proof of the property that this algorithm does work as expected. Now, there's typically, when we look at algorithms, two aspects to an algorithm that we need to ensure before we can say, yes, this algorithm is correct. The first aspect is an algorithm has to compute an output in finite time. That is, in other words, the algorithm doesn't run into an infinite loop or will continue computing forever, but at least in theory, even if it might take longer, we want to make sure that the algorithm is guaranteed to come to a conclusion. In other words, the algorithm terminates. This is an important property of this algorithm. We do know that we input two positive numbers, m and n. The algorithm does always terminate. Does anyone have an idea of how you can prove this? What is a good argument why we can be sure that this algorithm always terminates? Now, you have seen that in the example, when I started with 70 and 42, that I had to do a few steps. And it wasn't entirely clear how many steps I will have to take until I reach the m equals n case. So it's not as obvious as an algorithm that says, repeat this exactly 10 times, and then you're done. This, of course, is easy to see that this must terminate. But here, this rewriting, the arguments might go on forever. Or maybe not. Why can't it go on forever? Sorry?
Number m and n is not infinite.
Yes, so m and n are finite numbers. But even if I start with finite numbers, I could generate a process that will go on forever.
Eventually, it will be minus m and n will be less or equal to 0 if it is infinity loop.
So if it's an infinite loop, then yes, so that points in the right direction. If there was an infinite loop, if this process would go on forever, then eventually these numbers would become negative. Why can't these numbers ever become negative?
Otherwise, it won't suit for the algorithm.
Yeah, so I wouldn't follow the algorithm if I were to obtain a negative number. That's right. Of course, you could think of a slightly different process where I always subtract the second number from the first number, even if the second number is greater than the first number. Then I would easily obtain a negative number. But the way this algorithm has been designed is that I always subtract the smaller number from the larger number. And that means that I can never obtain a negative number by doing that. And since not every argument gets smaller, but there's always one of the two arguments that does get smaller, because by assumption m and n are greater than 0, I can be sure that eventually I reach either 1 for both, or I will reach the case where m equals n. So the actual proof is that these arguments together do get strictly smaller in every step, and they can never get to 0 or a negative number. Now, what you could do is you can implement this algorithm as a computer program. And I have done that here. As I said before, we are not, this is not a programming course. Occasionally, I will have a few programs, and I will freely switch between different programming languages. You will never have to worry about whether you understand or don't understand this programming language. All the programs that I will be looking at, they will be as small as this program. Now, for this particular program, I have chosen Python to implement this, assuming that many of you are also enrolled in the parallel course Introduction to Programming, where you will write programs of this syntax. But you can use any other programming language in order to implement the same algorithm. Here you can see I'm defining this function m and n, and I've got these three cases. If m is the same as n, return one of the two numbers. Else, if m is greater than n, subtract n from m, or do it the other way around. And then the rest of this program just asks for input, plus computes the output, f of x and y, and says the greatest common divisor of x and y is the result of applying this function. Now you can run this program with the Python interpreter. I called it euclid.python. It does ask you for an integer, for example 70 and 42, and it does compute 14 in exactly the same way as we have computed the greatest common divisor. Of course, if you do it the other way around, 42 and 70, then the result would be the same. Now remember that what we said about this proof is it terminates if we start with positive numbers. M and n have to be greater than 0. What do you think would happen if I were to use this algorithm to compute the greatest common divisor of minus 70 and minus 42? Would this also compute 14? Now, by definition, we know that the greatest common divisor of minus 70 and minus 42 should also be 14, just by definition, because it should always be positive. But would the algorithm compute it? The answer is no. We have said the algorithm terminates because we always subtract a smaller number from a larger number, and we always stay positive. But if we start with two numbers that are negative and we subtract numbers from negative numbers, then we actually do get smaller and smaller. And so what will happen is, if I try it with minus 42 and let's say 70, then you get this. So that only tells you that this would go on forever if I didn't have a finite computer where at some point the Python interpreter says, you are doing too many recursive steps. I don't think this will end ever. And this is why this program then basically crashes, because it would enter an infinite loop. Now, what could we do about this? Clearly, we could add an additional condition to make sure that every number that is negative and that the user inputs is first of all converted to a positive number, to make sure that this function f is only called with positive numbers. But it also shows, this particular example, how important it is that we are very clear about what input a function can take in order for us to be able to guarantee that the function works properly. And if you paid careful attention, you would have seen that the fact only applies to positive numbers. M and n have to be greater than 0, and only under this condition can we guarantee that the program, the algorithm, always terminates. Now, this is one aspect of the proof. We know that it terminates for positive input. The second aspect of the proof would be, how can we be sure that what we are computing is actually the greatest common divisor of not only 70 and 42, but of any two numbers that we input. And here is the mathematical proof that in order to understand, in order to be able to understand it, might be good to have another look at what we have done here when we applied this to a particular example. The reason why I wrote greatest common divisor here is also because mathematically what I have written here is not only the execution of this algorithm, but it's mathematical correct equations. That is, the greatest common divisor of 14 and 14 is really 14. I think this is obvious. 14 is a divisor of 14 and of 14, and of course it's the greatest common divisor. But it is also the case that the greatest common divisor of these two numbers is exactly the same as the greatest common divisor of 28 and 14. And that is the greatest common divisor of 28 and 42. And finally, this is also the same as the greatest common divisor of 70 and 42. So every time I've applied one step in this algorithm, I have calculated the exact same number. We can see that here, that 14 is the greatest common divisor of 70 and 42, 14 is the greatest common divisor of 28 and 42, and so on. But we can also say that this is true in general. And this is what this mathematical proof here tells us. The theorem says that for any two integers, m and n, if m is greater than n, the greatest common divisor of m and n is the same as the greatest common divisor of m minus n and n. So it makes a claim that basically every single step that I'm taking is justified by the fact that I'm computing exactly the same number. So if I subtract the smaller number, in this case n, from the larger number m, then the greatest common divisors are always the same, or is always the same. How can we ensure that this is the case? This is what this proof here says. It does make an even bolder claim. It says not only is the greatest common divisor the same for these two numbers, but as a matter of fact, these two pairs of numbers have all divisors in common. That is, every d is a divisor of both m and n, if and only if d is a divisor of m minus n and n. Now, if we say that the set of divisors, all divisors of the first pair, is the same as all the divisors of the second pair, then clearly it follows that the greatest of these two must be the same. If they share all the common divisors, then they surely have the greatest common divisor in common. Now we have this to prove. We have to say that every divisor of both m and n, every divisor of m and n, is also a divisor of m minus n, and vice versa. Now, a proof of this if and only if we can divide into two different steps. The first step is, so to speak, an implication in this direction. That is, if we are given that d divides m and d divides n, can be sure that d divides m minus n and n. Now, clearly, if we're given that d divides n, then we know that d divides n. So the important part of this proof is, if d is a divisor of m and n, is it also a divisor of the difference between the two? And we can formally prove this by applying the definition of being a divisor, which says that if d divides m and d divides n, then we know there must be an integer a and an integer b, so that if we multiply d with a, we obtain the first number. If we multiply d with b, we obtain the second number. So we can always find these two numbers, a and b, so that we obtain m and n. And if you find that hard to follow, then I suggest that you apply the example. You try it with 70 and with 42, and for example, the divisor 7. If 7 is a divisor of 42 and 7 is a divisor of 70, then you can find these two numbers a and b, and it might be a nice exercise for you to think about what a and b would be, so that this is really the case. Now, if that is the case and this is the case, then we can calculate the difference between m and n as a times d minus b times d. And clearly, a times d minus b times d is the same as, simple arithmetic, a minus b times d. Now, what does that tell us? It tells us that we can find a third number, namely a minus b, so that when we multiply the divisor d by a minus b, we obtain m minus n. And this is exactly what we needed to know. We wanted to make sure that d is also a divisor of m minus n. And with this, we have proved, formally, mathematically, the first part of this statement here, namely, if d divides m and n, then we can be sure that d divides m minus n and n. That's the first part. The second part would be do it the other way around. Here we claim that the divisors are identical, so we also have to make sure that every d that satisfies this and this does satisfy this. And indeed it does. I won't be going through this in detail because it would be more or less a repetition of this case, but it might be a very good exercise for you to fill these dots and formally prove that this is indeed the case. And further on, there will be another exercise on this week's problem set where I give you a slightly different version of Euclid's algorithm, which tends to be much faster for most numbers. And then it is a very interesting exercise to see whether you can, in the very same way as we proved that this algorithm is correct, that you can make absolutely clear and sure that this alternative version of Euclid's algorithm is also correct. So that gives you an example of applying this mathematical reasoning and the definitions that we have to a given algorithm to ensure that this algorithm does exactly what we expect it to do. Now, let's move on from numbers to yet another very basic concept for mathematics as well as in particular for computer science. We will be talking about or defining sets. Sets of arbitrary elements, not necessarily numbers. We've already seen sets of numbers like the real numbers, the integers. But we will also be considering sets as a more general concept. Sets can typically be defined in two different ways. You can, first of all, explicitly enumerate these elements. And here's a very simple example. We have a set with 3 elements, A, B, and C. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, Then there's an important property of sets that we don't really care in which order you write down the elements of a set. So this set would be the same as this set. It also has the 3 elements A, B, and C. It would also be the same as this set, if you like. You can repeat numbers or elements in general. It wouldn't make a difference. This set here, again, has A, B, and C as elements, and it does not have 6 elements. It's still the 3, A, B, and C. Now, a little more interesting is sets can also have sets themselves as elements. And as computer scientists, we always have to be very careful about specifications like this, because when we use the concept of a set as a data structure in a computer program, and we tell a function that the input that you have is a set of numbers or a set of sets of numbers, then it makes a big difference, and you can't call the function with the wrong type of input. So this set here consists of 2 elements. It consists of the element A itself and an element that is very different from the element A, namely a set which contains the element A. So this element is very different from this first element. And therefore, this set does have 2 elements, one which is a letter and the other is a set. Similarly here, we've got 3 elements, 2, if you wish, regular elements, and 1 set. This set here, with just the 2 braces, indicates an element or a set without an element, the so-called empty set, 0 elements. And here I'm doing something really very strange. I've got a set that contains only 1 element, and that 1 element is a set that contains only 1 element, namely the empty set. So it's a set of sets, and it contains exactly 1 element, because this here is the empty set. It contains no element, but this set here is the set that contains the empty set and therefore has 1 element. And this set that contains the empty set is also the element of this set here. And again, for both a mathematician as well as a computer program, these are different things. The set that contains the empty set is of a different type than the set that contains the set that contains the empty set. And you can find really strange constructions. Whether they are practical or not is a different question. But this set here would have 2 elements, the empty set and this set that contains the empty set. Now, this is the standard notation for saying that an arbitrary object X is an element of a set. It is this symbol here that indicates that it belongs to the set or is an element. This is one way of denoting sets. The probably more useful way of specifying sets, which you would normally use when you specify properties of programs or you provide specifications of a problem, then you would, rather than explicitly listing all the elements, you would specify the properties that the elements of a set must satisfy. If you do this, then typically the elements are taken from some universal domain, where this universal domain is either clear from the context or it is specifically stated where these elements should come from. And then a typical description, implicit description of a set would look like this. It would say, I'm defining a set S as the set that contains all elements of the form X, which come from a universal context and do satisfy a certain property. For example, you can say, I want to define the set of all even integers. Then you would say, I'm talking about integers, and the property that my elements have to satisfy is that 2 is a divisor of these elements. Shorthand notation would be saying X in capital X. For example, X is in Z, all our integers, so that 2 is a divisor of X, or in general, they have to satisfy the property P. Always make sure that you distinguish between an element itself and the set that comprises or contains this as a single element. So always an element A is very different from the singleton set that contains A. And just to reiterate what I said on the previous slide, this set here is empty and contains 0 elements, whereas this set is not empty. It contains 1 element, namely the element, the empty set itself. And there is only one empty set. There's only one set that consists of a single A, and there's only one set of, for example, all natural numbers. We can construct sets from other sets in case these other sets have already been defined. We can define the usual operations on set, can build the union, the intersection, the set difference. Sometimes we might be interested in the so-called symmetric difference, and the complement of a set. I will define this formally shortly, or possibly at the beginning of tomorrow's lecture, but union and intersection is in no way different from what most of you would understand intuitively from either high school or previous studies. But as I said, I will define this formally a little later. We can also build the power set of a set, slightly more interesting. The power set of a set X will be all sets A, so that A is a subset of X, subset or equal. Now, what do I mean by subset? This is this notation here. S is a subset or equal to T. It means that every element in S is also an element in T. And it does include the case that the two sets are equal. This is the standard symbol for saying that S is a proper subset, meaning that every element in S also occurs in T, but they are not equal. So there are some elements in T that are not in S, and that would cover this case here. So that's the definition of this power set. It takes all subsets of an element. We can also define the Cartesian product. I will define that a little later. And we do have the empty set, for which there is an alternative notation, and this is this here. Now, in the literature, you will find this as often as you will find these two braces without anything in between. Both of these are notations that can be used, and they mean the same thing. They mean the set that contains no elements, and this set does have the property that it is a subset of every other set, simply because clearly every element in the empty set is also an element of X, because there is nothing to check. Empty set will always be a subset of X. Now, given all this, the, again, distinction between sets and individual elements. A would be an element of this set A and B, but A would not be a subset of A and B. Why is that not a subset of A and B? Well, A itself is not a set. A is an element, but it's not a set, so it can't be a subset. You can't even ask the question whether all elements in A are in this set. Conversely, the set that contains A is a proper subset of A and B, because every element in here is also an element in here, whereas this set is not an element in this set, simply because this set only contains regular letters as elements and not sets as elements. If that sounds trivial, then that's perfectly fine. Make sure, however, you understand exactly what this means so that you are clear about the distinction between sets and elements on the one hand, and being an element of a set and being a subset of a set. We often will talk about the cardinality of a set, which tells us or says what the number of elements in a set are. There are various notations that you will find in mathematics and in particular in computer science. A standard notation would be the same as for the absolute value, which might be a bit confusing, but from the context, it would always be clear whether you're talking about an absolute value of a number like -3, or whether you're talking about the number of elements in a set. Sometimes you will find this notation indicating the number of elements in this X, or card of X for cardinality is a notation that is always that is often used. What can we say about the size of various sets? For example, a particularly important property is that the size of the power set of a set X is always 2 to the power of X. So if you've got a set with 3 elements, then there are exactly 8 subsets of this set. Starting with the empty set, then we've got all the singleton sets, like A, the set that contains A is a subset of A, B, C, and so on. You will find exactly 8 subsets of a set that contains 3 elements. This even applies to the boundary cases. The empty set has 0 elements. The power set of the empty set, that is the set of all subsets of the empty set, actually does have 1 element. And that is because the empty set itself is a subset of the empty set. So the power set contains this 1 element. Now, if you take the power set of the empty set, that is the set of all subsets of this set, you will actually obtain 2 elements. The empty set itself is always a subset of any set, but also this here is a subset of this set. And therefore, the power set of the power set has 2 elements, which is 2 to the power of 1. If you wish, you can continue this and see that this set here has exactly 4 subsets. Now, for a single set, we always have that it contains 1 element, and the power set of this singleton set will contain 2 elements, the empty set and the set itself, and therefore, again, contain 2 elements, and so on. This is the notation for cardinality. Then one more notation for an interval of integers. We use these square brackets. This really is standard notation, which you would find everywhere when someone talks about an interval. This interval between m and n, if m and n are integers, would mean all the integers that are between m and n. For example, between 5 and 15, you would have exactly 11 numbers, including 5 and 15. And by definition, the interval would be empty if the left boundary is actually larger than the right boundary. So if someone writes down the interval from 15 to 10, it actually contains no number. The the number of elements in an interval will always be the difference between n and m plus 1. I just gave you an example. 5 to 15 would contain exactly 11 elements because you have to count both 5 and 15. Sets of numbers we have already seen. We have seen integers for which we use this z. We can introduce a few more sets of numbers. The natural numbers, usually denoted by this symbol, would be all the positive integers including 0, whereas all the strictly positive integers, sometimes denoted by this funny capital P, would be almost the same as the natural numbers, but not contain 0. 0 is not defined as a positive integer. Sometimes you will see notations like this, the natural numbers that are greater than 0, which would be all natural numbers except for 0. This little symbol, I will also introduce later formally, means everything in this set except for this argument. It's the so-called set difference function. And this would be the same as all the integers z that are strictly greater than 0. Again, this would be 1, 2, 3, and so on. Integers we have defined earlier. It's all the positive numbers, including 0, plus 0, plus all the negative integers. And then we can define the so-called rational numbers or fractions, for which the standard symbol would be this Q, which contains all the fractions that you can construct from integers. So it would contain a number like 1 over 3 or 0.5, which is 1 over 2. But it doesn't contain all real numbers, because there are the so-called irrational numbers like pi or the square root of 3. These would be the real numbers, and they have already been, for those we have already introduced the notation capital R, which means all the real numbers that could be written in this form with the decimal point, or you could even, as computer scientists, use just zeros and ones, and this can go on forever. So it includes not only rational numbers like 1 over 3, but also irrational numbers like pi. An interesting property of the positive numbers, the natural numbers and the integers, is that different symbols denote different numbers. 3 is not the same as 4. But in Q and R, the standard representation is not necessarily unique. And this is clear. 1 over 3 could also, or is the same as 2 over 6. Or 0.333 forever could also be written as 1.3. Or a funny fact is that 0.9999 is the same number as 1. A few simple exercises on these definitions. Find out how many numbers are in this set. So this is a set that is implicitly defined. We say this set contains all the rational numbers 1 over n, where n comes from the interval 1 to 4. How many elements are in this set? 4, yes. So it's 1, 0.5, 1/3, and 1 over 4. How many elements do we have in this set? N squared minus n. Again, n comes from this interval 0 to 4. Is it again 4? Is 3? 3, 4, 4. Yes, it is 4. It is not 5, although we have 5 possibilities for n. But there's one number that is defined twice, namely 0 squared minus 0 is 0, and 1 squared minus 1 is also 0. So when you write down the elements of this set, you would say 0, comma 0 again, which doesn't add anything to the set. And then you've got 4 minus 2 is 2. You've got 9 minus 3, which is 6, and 16 minus 4, which is 12. And this is exactly 4 elements. What about this set? We have only positive integers, n, and we take 1 divided by n squared, where n is a positive integer, and it has to be an even number. So 2 has to be a divisor of n, and n should be smaller than 11. How many elements do we have here? 5, yes. It's exactly 5 numbers, because they will all be different. And we've got 2, 4, 6, 8, and 10 as even numbers that are smaller than 11. What about this set? 2 plus minus 1 to the power of n for any natural number n. So 2 or 3. What would be 2 numbers? 1 or 3. So 2 plus, either this is plus 1, if n is even,